Hi viewers, good morning and assalamu alaikum. Today we are going to discuss the topic is green chemistry. Green chemistry is an inventive science based on fundamental research towards the development of new sustainable chemical processes. There is a great need to create a new type of chemistry focused on a new production system in order to prepare the younger generation to get a greener future. With this few introduction, we go to next slide. The content of green chemistry is introduction, definition, needs of green chemistry, and 12 principles of green chemistry. The term green chemistry, also called sustainable chemistry, is defined as the invention, design, and application of chemical products and to reduce or to eliminate the use and generation of hazardous substance. While this short definition appears straightforward, it marks a significant departure from the manner in which environmental issues have been considered or ignored in the upfront design of the molecule and molecular transformation that are the heart of the chemical enterprise. Looking at the definition of green chemistry, the first thing one sees is the concept of invention and design. By requiring that the impact of chemical products and the chemical process are included as design criteria, the definition of green chemistry links hazard consideration to performance criteria. Another aspect of definition of green chemistry is found in the phrase use and generation, rather than focusing only on those undesirable substances that might be inadvertently produced in a process. Green chemistry also includes all substances that are part of the process. Therefore, green chemistry is a tool not only for minimizing the negative impact of those procedures aimed at optimizing efficiency, although clearly both impact minimization and process optimization are legitimate and complementary objectives of the subject. Green chemistry, however, also recognizes that there are significant consequences to the use of hazardous substances, ranging from regularity, handling and transport and liability issues, to name a few. To limit the definition to deal with waste only would be to address only part of the problem. Green chemistry is applicable to all aspects of the product life cycle as well. Finally, the definition of green chemistry includes the term hazardous. It is important to note that green chemistry is a way of dealing with risk reduction and pollution prevention by addressing the intrinsic hazards of the substances, rather than those circumstances and the conditions of their use that might increase their risk. The next one, need of green chemistry. The dangers associated with chemicals and chemical reaction motivated chemists to develop methodologies and formulate strategies to carry out chemical reaction in a safe and environmentally benign manner. Such chemical reaction carried out by environmentally benign process are known as green reaction, and the area of chemistry involved in designing this reaction is known as green chemistry. Green chemistry is the utilization of a set of principles that reduces or eliminates the use of generation of hazardous substances in the design, manufacture, and application of chemical products. However, later on some more relevant and useful issues were also included in the theme of green chemistry. The concept of green chemistry should not be confused with that of environmental chemistry. The former is related with the design of chemical products and processes in a less hazardous manner, while the latter deals with the study of various chemical reaction takes place in atmosphere. In fact, green chemistry started in 1990s as a mission in developed countries to make chemistry and chemical reaction safe and hazardless up to the maximum extent. Green chemistry is concerned not only with safety and pollution control, it gives due consideration due to quality and cost of the products and efficiency of the adopted procedure as well. To make it more practical and widely acceptable, chemists all over the world are searching alternative reagents, solvents, catalysts, and newer techniques. The next one, principles of green chemistry. The principles cover such a concept as prevent waste. The ability of chemists to redesign chemical transformation to minimize the generation of hazardous waste is an important first step in pollution prevention. By preventing waste generation, we minimize hazards associated with waste storage, transportation, and treatment. The next one, minimize atom economy. Atom economy is a concept developed by Barry Trost of Stanford University that evaluates the efficiency of a chemical transformation similar to a yield calculation. Atom economy is a ratio of the total mass of atoms in the desired product to the total mass of atoms in the reactant. One way to minimize waste is to design chemical transformation that minimize the incorporation of all materials used in the process into the final product, resulting in few of any wasted atoms. Choosing transformation that incorporate most of the starting materials into the product is more efficient and minimize waste. The next principle, designless hazardous chemical synthesis. Wherever practicable, synthetic methodologies should be designed to use and generate substances that possess little or no toxicity to human health and environment. The goal is to use less hazardous reagents wherever possible and design processes that do not produce hazardous byproduct. Often a range of reagent choices exist for a particular transformation. This principle focuses on choosing reagents that pose the least risk and generate only benign byproducts. The next principle is design safer chemicals and products. Chemical products should be designed to affect their desired function while minimizing their toxicity. Toxicity and ecotoxicity are the properties of the product. New products can be designed that are inherently safer while highly effective for the target application. In academic laboratories, these principles should influence the design of synthetic target and new product. Next one, use safer solvents reaction conditions. The use of auxiliary substance, example solvent, separation agent, etc., should be made unnecessary wherever possible and innocuous when used. Solvent use leads to considerable waste. Reduction of solvent volume or elimination of the solvent is often possible. In cases where the solvent is needed, less hazardous replacements should be used. Purification steps also generate large sums of solvent and other waste. Avoid purification when possible and minimize the use of auxiliary substances when they are needed. The next, increase energy efficiency. Energy requirement of chemical processes should be organized for their environmental and economic impacts and should be minimized. If possible, synthetic and purification method should be designed for ambient temperature and pressure so that energy cost associated with the extremes in temperature and pressure are minimized. The next principle is use renewable feedstocks. Whenever possible, chemical transformation should be designed to utilize raw materials and feedstocks that are renewable. Example of renewable feedstocks include agricultural product or the waste of other process. Example of depleting feedstocks include raw material that are mined or generated from possible fuels. For example, petroleum, natural gas, coal, etc. The next principle is avoid chemical derivatives. Unnecessary derivatization of should be minimized or avoided if possible because such steps require additional reagent and can generate waste. Synthetic transformation that are more selective will eliminate or reduce the need for protecting groups. In addition, alternative synthetic sequences may eliminate the need to transform a functional group in the presence of other sensitive functionality. The next is use catalyst. Catalytic reagents are superior to stoichiometric reagents. Catalysts can serve several roles during a transformation. They can increase the selectivity of a reaction, reduce the temperature of transformation, enhance the extent of conversion to product and reduce reagent based waste. By reducing the temperature, one can save energy and potentially avoid unwanted side reactions. The next principle is design for degradation. Chemical products should be designed so that at the end of their function they break down into the innocuous degradation products and do not persist in the environment. Efforts related to this principle focus on using molecular level design to develop products that will degrade into hazardous substances when they are released into the environment. Next one, analyze in real time to prevent pollution. It is always important to monitor the progress of a reaction to know when the reaction is complete or to detect the emergence of any unwanted byproducts. Whenever possible, analytical methodologies should be developed and used to allow for real-time in-process monitoring and control to minimize the transformation of hazardous substances. The next last principle is minimize the potential for accident. One way to minimize the potential for chemical accident is to choose reagent and solvents that minimize the potential for explosion, fire and accidental release. Risks associated with this type of accident can sometimes be reduced by altering the form or composition of the reagents. Thank you.